Have you ever imagined something being two things at once? In quantum mechanics, that's not just possible. It's a rule. Picture a cat inside a sealed box. You can't see or hear it. Is the cat alive or dead? What if, until you open the box, it's both? This is Schrödinger's cat, a thought experiment from 1935 that shows how bizarre quantum rules can be when applied to everyday objects. In our world, things are definite. A light switch is on or off. A coin is heads or tails. But in the quantum world, things can be a fuzzy mix of all possibilities until we look. Schrödinger's cat bridges the quantum realm of probabilities and our world of certainties. Ready to peek inside the box? Let's dive in. Let's build the experiment. We have a sealed box with a cat inside. The cat's fate depends on a single radioactive atom, which might or might not decay within an hour. If the atom decays, a Geiger counter detects it, triggering a hammer to smash a vial of poison, ending the cat's life. If the atom doesn't decay, nothing happens and the cat lives. The entire setup is a chain reaction, media group, flowchart or diagram, showing chain reaction from atom decay to cat, with clear arrows and labels at stock at distribute _ equally. Atom decays, Geiger counter clicks, hammer falls, poison is released, cat dies. If the atom doesn't decay, the Geiger counter stays silent, the hammer doesn't move, and the cat is fine. The cat's life or death is now tied to the quantum state of a single atom. The big world is now linked to the small world. This experiment shows how quantum uncertainty can affect something as large as a cat. It's a macabre but brilliant way to reveal quantum strangeness. So what does this mean for reality? Here's the quantum twist. Until we check, the atom is in a superposition, both decayed and not decayed. Like a spinning coin that's both heads and tails until it lands, the atom is both states at once. Schrödinger linked the cat's fate to this superposition. If the atom is both decayed and not, then the cat is both dead and alive. It's not just that we don't know. The theory says the cat truly is both. This feels impossible, but in the quantum world, it's normal. The cat state is described by a wave function, a mathematical blend of all possibilities. Schrödinger's cat highlights the clash between quantum possibilities and our everyday reality. He wanted to show how strange quantum rules become when scaled up. The experiment forces us to confront the weirdness at the heart of physics. So, what makes the cat alive or dead? Measurement. When you open the box, the superposition collapses. The cat becomes either alive or dead. This is called wave function collapse, and it's the heart of the measurement problem in quantum physics. Most physicists say any interaction with the outside world counts as a measurement, not just a conscious observer. In quantum experiments, the act of measuring always changes the system. There's no such thing as a passive observer. Schrödinger's cat led to two major interpretations of quantum mechanics. The Copenhagen interpretation says the cat is truly both alive and dead until observed. Measurement forces a random choice. It draws a line between the quantum and classical worlds, but doesn't explain why collapse happens. The many worlds interpretation, proposed by Hugh Everett, says there's no collapse. Instead, every possible outcome happens in a branching universe. In one universe, the cat lives. In another, it dies. Both outcomes are real, just in separate realities. You only experience one, but another, you experiences the other. These ideas show just how strange and unsettled quantum reality remains. Schrödinger's cat isn't just a thought experiment anymore. It's inspiring real technology quantum computers. Classical computers use bits, zeros or ones. Quantum computers use qubits, which can be 0, 1, or both at once, thanks to superposition. This lets quantum computers process vast possibilities simultaneously. But qubits are fragile. Any disturbance collapses their superposition, a problem called decoherence. Engineers must keep qubits isolated, just like the cat in its box. The challenge Schrödinger imagined is now a real engineering problem. Quantum computers could revolutionize medicine, materials, and cryptography. Quantum mechanics isn't just theory, it powers your daily life. Microchips in your devices rely on quantum rules to work. Transistors, the building blocks of electronics, only function because of quantum effects. MRI machines use quantum spin to see inside your body. Lasers, GPS, and even the sun's energy all depend on quantum physics. The quantum world is the foundation of modern technology. Every time you use a digital device, you're benefiting from quantum science. The weirdness of Schrödinger's cat is everywhere, shaping our world. Why do we keep talking about Schrödinger's cat? Because it's the ultimate test for any new quantum idea. The cat forces us to ask, what is real? Do we create reality by observing it? The paradox inspires scientists and engineers, especially those building quantum computers. Keeping qubits in superposition is just like keeping the cat both alive and dead. The puzzle of yesterday is the engineering challenge of today. Schrödinger's cat reminds us to stay curious and humble. Reality is stranger than we think. We've explored a cat-in-a-box, quantum superposition, and the mysteries of measurement. The principles behind Schrödinger's cat are now driving a technological revolution. Quantum computing is about keeping qubits in that delicate both-at-once state. The universe isn't a predictable machine. It's a place of probabilities and surprises. Schrödinger's cat stretches our minds and reminds us to keep questioning. The world is full of wonders just beyond our senses. The universe owes us no simplicity, and that's what makes it so exciting.